Welcome to Chem Talk. Today, we're diving deep into something pretty fundamental for understanding, well, all the stuff around us.
Yeah, we're talking percent composition and also percent water in hydrates.
Right. Think about, like, your favorite snack mix. You know how the label might say, okay, 40% peanuts, 30% almonds, that kind of thing.
Exactly. That's pretty much what percent composition is, but, on a chemical level. We're figuring out what percentage of a compound's mass comes from each different element inside it.
So that's kind of our mission today, right? To really get a handle on this concept.
Totally. And we've got some good stuff to help us unpack it, textbook bits explaining the math, some really useful videos too.
And we'll definitely get into hydrates. Those are super interesting compounds, the ones with water molecules sort of hiding inside their crystal structure.
It's almost like water is baked right into the recipe.
Yeah.
You might be surprised how much water can be in something that looks totally solid and dry.
Yeah, it's pretty wild. And we'll try to connect this to things you might already know, maybe even some pop culture stuff like video games or movies.
Get ready for some aha moments, hopefully, as we unlock these ideas.
Okay, let's dive in. Percent composition, you said it's the percent by mass of each element.
Exactly, percent by mass. So back to the snack mix example, if you have 100 grams total and 40 grams of that is peanuts, then peanuts make up 40% of the mass.
Simple enough, so chemists do the same thing, but with elements in a chemical compound.
Precisely. And one way they figure this out is just by measuring stuff, getting mass data from an experiment.
How does that work?
Okay, imagine a chemist just made a new compound. Let's say it's made of zinc, Zn, and oxygen, O.
Okay, a zinc-oxygen compound. Shiny.
Maybe. So they have a sample, let's say exactly 20 grams of this new stuff.
Yep.
And they decide to break it down, decompose it completely.
Back into pure zinc and pure oxygen?
Well, they manage to separate out the zinc, and they find they have 16.07 grams of just zinc metal.
Okay, so 16.07 grams of zinc out of a 20.00 gram sample. How do you find the oxygen part?
Simple subtraction, right? If the total was 20.0 grams and the zinc part was 16.07, the rest must have been oxygen.
Ah, so 20.000 minus 16.07, that's 3.93 grams of oxygen.
You got it. 3.93 grams of oxygen. Now we have the mass of each part.
So how do we get the percentages from those masses?
Right. For the percentage of zinc, you take the mass of the zinc that was 16.07 grams divided by the total mass of the compound, 20.00 grams.
Okay, 16.07 divided by 20.0.
And then critically, multiply by 100% to make it a percentage.
Gotcha. So 16.07, 20.00 times 100, that's 80.35% zinc.
Perfect. You do the exact same thing for oxygen. Mass of oxygen, 3.93 grams divided by the total mass, 20.00.
Times 100% gives 19.65% oxygen.
Exactly. And a good way to check your work is to add the percentages up.
Let's see, 80.35 plus 19.65. Yep, that's exactly 100%. It all adds up.
It should always add up to 100, or, really close depending on rounding. It tells you you've accounted for everything.
It makes sense. It's like knowing all the ingredients are accounted for.
And thinking bigger picture for a sec. People talk about how the Earth is like 70% water, right?
Yeah, and our bodies too, roughly.
Right. And even more fundamentally, our bodies are mostly made of just a few elements: oxygen, carbon, hydrogen, nitrogen. Percent composition helps us understand those basic building blocks, the proportions of elements that literally make us up.
So it's not just lab chemicals, it applies to...
Well, everything.
Yeah.
Now, what's really neat is that you don't always need to do an experiment to figure this out.
Oh, how else can you do it?
If you know the chemical formula of the compound, it's like having the recipe.
You mean like H20 for water?
Exactly.
Yeah.
Or
Yeah.
let's take something slightly more complex, like
Able.
dichlorine heptoxide. Fun name, right? Cl2O7.
Cl2O7. Okay, 2 chlorines, 7 oxygens. How does the formula give us percentages?
Well, first you need the molar mass of the whole compound. Remember molar mass. It's the mass of 1 mole of that substance.
Yeah, like grams per mole. You get the atomic masses from the periodic table and add them up based on the formula.
Exactly. So for Cl2O7, you'd look up chlorine, Cl, and oxygen, O. Chlorine's about 35.45 gamma, and there are 2 of them, so that's 70.90 grams from chlorine.
Okay, and oxygen is about 16.00, these times 7, is 112.00 grams from oxygen.
Right, so the total molar mass of Cl2O7 is 70.90 plus 112.00, which is 182.90 grams per mole.
Got it. So that's the mass of 1 mole of the whole compound. How does that help with percentages?
Now, it's just like the mass calculation we did before, but using these molar masses. Define the percent chlorine.
Would it be the mass of the chlorine part divided by the total molar mass?
You nailed it. Mass of chlorine in 1 mole, 70.90, divided by the total molar mass, 182.90 mole, then
Yeah.
times 100%.
Okay. 70.90 divided by 182.90 times 100 works out to about 38.76% chlorine.
Perfect. And for oxygen?
Same logic. Mass of the oxygen part, 112.00 grams divided by the total, 182.90 grams times 100%.
Which gives you?
61.24% oxygen.
Exactly. And again, check it. 38.76 plus 61.24 is 100%. It works out perfectly.
That's actually pretty slick. So if you know the formula, you can figure out the percent composition without even touching the chemical.
Right. It's powerful. And you can use this knowledge, too.
How so? Like, what's the point of knowing the percentage?
Well, let's say you have a specific amount of that dichlorine heptoxide, say 12.5 grams.
Okay, a 12.3 gram sample.
Since you know it's 38.76% chlorine by mass, you can calculate exactly how many grams of chlorine are in that sample.
Oh, right. You just multiply the total mass by the percentage, but as a decimal.
Exactly. So 12.5 grams times 0.3876
is 4.845 grams of chlorine.
Yep. And for oxygen, it's 12.5 grams times 0.6124.
Which is 7.655 grams of oxygen.
And if you add those two masses, 4.845 plus 7.655.
You get 12.5 grams. Back to the original sample mass. That's neat. It's like chemical accounting.
It really is. You know exactly what you have in terms of the elements.
This kind of reminds me of, like, analyzing stats in a video game.
How so?
Like, if you have a superhero team or maybe characters in an RPG, percent composition is like knowing what percentage of the team's total power comes from the healer, what percentage from the tank, what percentage from the damage dealer.
That's a great analogy, yeah. Or if you have some super alloy in a sci-fi movie, knowing the percent composition tells you how much of each rare, powerful element makes it up.
And if you know the total strength of the team or the total mass of the alloy and the percentages,
you can figure out the individual contribution of each member or element.
Exactly. Whoa, okay, so that's percent composition. Now, what about this other thing you mentioned? Hydrates. What exactly is a hydrate?
Right, hydrates. These are ionic compounds, usually salts, that have a specific number of water molecules trapped within their crystal structure.
Trapped, like physically stuck.
Well, they're incorporated into the repeating pattern of the crystal lattice. They're chemically associated, not just like wet on the surface.
Okay. Can you give an example?
Sure. A classic one is cobalt chloride hexahydrate. Its formula is written CoCl2 6H2O.
CoCl2 dot 6H2O. What's the dot mean?
The dot basically signifies that the 6 water molecules, 6H2O, are associated with one formula unit of cobalt-2 chloride, CoCl2, within the crystal structure. It's not a multiplication sign. It just shows they're bound together in the hydrate.
So for every CoCl2 unit, there are 6 water molecules hanging out with it in the crystal.
Pretty much, yeah. They're integral to the structure.
I feel like I've heard about these. Don't some of them change color depending on if the water is there or not?
You're totally right. That's one of the coolest things about hydrates. Think about copper-2 sulfate. You usually see it as these nice blue crystals, right?
Yeah, the blue one.
That's actually copper-2 sulfate pentahydrate. It has 5 water molecules, QSO4FA5H2O. If you heat it up,
you drive water off.
Exactly. And it turns into a white powder. That white powder is anhydrous, copper, sulfate anhydrous, meaning without water. The blue color comes from the water being part of the crystal structure.
Whoa. So the water itself causes the color?
In a way, yes. It changes the environment around the copper ion, which affects how it absorbs and reflects light. Same thing with our cobalt example. The anhydrous CoCl2 is blue, but the hexahydrate, CoCl2 6H2O, is this really vibrant magenta color.
That's awesome, like a built-in moisture indicator.
Yeah.
Okay, so how do we calculate the percent water in one of these hydrates?
It's actually the same principle as percent composition by element, just applied to the water part.
So mass of the water part divided by the total mass of the hydrate times 100.
Exactly. Let's use the cobalt-2 chloride hexahydrate, CoCl2 6H2O. First, we need the mass of the water part in 1 mole.
Okay, one water molecule, H2O, has a molar mass of about 18.015 grams per mole, let's say.
Good. And the formula says there are 6 water molecules, the 6H2O part.
So 6 times 18.015 gmol. That's 108.09 grams per mole just from the water.
Right. That's the mass of the water part in 1 mole of the hydrate. Now we need the total molar mass of the whole hydrate, CoCl2 6H2O.
Okay, we need the mass of the CoCl2 part first. Cobalt is about 58.93. Chlorine is 35.45 times 2. Adds up to around 129.83 or 129.84 gmol for CoCl2.
Perfect. Let's use 129.84 gmol. Now to get the molar mass of the hydrate, we just add the CoCl2 part and the water part together.
So 129.84 gmol plus the 137.93 grams per mole for the whole CoCl2 6H2O shebang.
Exactly. That's the total molar mass. Now for the final step, the percent water.
Okay, mass of the water part, 108.09, divided by the total mass of the hydrate, 237.93 times 100%.
Crunch those numbers.
Let's see, it's about 45.43% water.
Isn't that something? Almost half the mass of those magenta crystals is just water molecules integrated into the structure.
Wow, that's way more than I would have guessed. It's like finding hidden water weight.
It really is. Let's try one more, maybe the one from the video. Calcium sulfate dihydrate, CoSO4.2H2O.
Okay, KSO4.2H2O, 2 water molecules this time.
Right. So the mass from the water part is 2 times, let's use 18.02 gmol for water this time, like in the video.
So 36.04 gmol from the water.
Yep. Now the KSO4 part. Calcium is about 40.08, sulfur 32.07, oxygen is 16.00 times 4.
Adding those up, 40.08 plus 32.07 plus 64.00 equals 136.15 new mole for the KSO4.
Good. So the total molar mass of the hydrate, KSO4 2H2O, is 136.15 plus the 36.04.
Equals 172.19 grams per mole. Might be slightly different from the video due to rounding, but close.
Yeah, atomic masses can vary slightly depending on the source. So using our numbers, the percent water.
Mass of water, 36.04, divided by total mass, 172.19 times 100, gives about 20.93% water.
Still a pretty significant chunk. About 1/5 of the mass is water.
This is really making me think about those video game characters again.
Oh, yeah.
Like maybe a character whose power is based on water, like a water mage or something. The hydrate is like the character, and the percent water calculation tells you exactly how much of their total mass or power potential comes specifically from that water element.
That's a perfect analogy.
Mhm.
Hydrates are literally compounds with water power built into their structure, and knowing the percentage is key.
And you mentioned heating them changes their properties, like the color change.
Yeah, driving off that water can fundamentally change how the compound behaves, which is used in chemistry for various things like drying agents or indicators.
So, wow. Whether it's figuring out what elements make up some new material or understanding why heating blue crystals turns them white, these concepts, percent composition and percent water in hydrates, they're really fundamental tools.
Absolutely. They help you break down matter and understand its makeup on a molecular level.
Yeah.
You now have a much better idea of how chemists quantify what stuff is made of.
It makes you think differently about, well, everything, like the ingredients in medicine or the materials in your phone. What's their percent composition?
Could any of them be hydrates? Are there hidden water molecules influencing their properties? It opens up a lot of questions.
This deep dive has been really illuminating, I think. Hopefully it's given you listening a solid foundation.
But like you said, it's just scratching the surface. There's a whole world of chemical analysis out there.
Definitely sparked my curiosity more. And hey, a special shout out to the Geeky Gamer science teacher for creating this awesome podcast.